Okay, last call. All right, here's the deal. This is the second one. That's the first one, I think. Oh, it looks like some people turned them in together. Yeah, this is the second one. All right, at the end of class last time, I said that I would email you your homework assignment, right? And I did, but then I changed it from a homework assignment to a quiz. So if you didn't check your email and you had no idea that there's another quiz due today, that's on you. All right. So this is my last call for quizzes. I will not take them after this. You can bring them to office hours, but I need what you have now. You can talk to me after class, but I need to see what you've done walking into class today. This is the second one. All righty. What I'm trying to get you all prepared for is the expectation level here in this class. Okay, just if you're struggling just to get these quizzes in, the pace of this course is so fast that it's going to be a continued struggle. So I'm just trying to get you like in the right gear here to start. If you're already like, oh, I didn't check my email, I have no idea, I'm not ready for today, you either need to switch gears or consider possibly that this may not be the right thing for you this semester, right? Because it's just going to get more challenging. What are we doing today? Questions? Any questions? Yes.
I saw that you put the videos on YouTube, but they're like not organized for our class. I don't know what they're trying to do.
Okay, yeah, I'm glad you brought that up. I did change, and I'm no longer using the same server for our videos. I've switched over to YouTube. So let me get logged in. I was going to show you this. I'm glad you reminded me. Get in there. What's that? I'm hardwired. Yeah. I might have just lost it the first time trying to open it up. So I'm not trying to discourage y'all with what I'm saying about staying on track. I want all of you to succeed in here. But you have to be realistic. If you don't have the time, you can't put in the effort, then it may not be realistic for you to say, oh, I'm going to do Cal 2 this semester. Because the time you have to put in is significant. I don't know, maybe Northwest Vista's website's down. Would that surprise you? You try and get directly into ACES. Okay, here we go. Yeah, that's what I heard too. All right, so here we go. You go to our class, right? And I understand this is a lot of crap in here, okay? But I'm trying to give you as much resources as I can. The first one here, our recorded class lectures. That's what I'm doing right now, recording, okay? Click on that, it'll take you there. This is my old Cal 2 class, my old Cal 1 class, and then some other stuff I made for Cal 1. So now if you click on ours, it'll bring you to this little YouTube. It's like embedded in Canvas. And right here, there's a drop down for playlist. And you should be able to see, it's not coming through very good on this screen because I'm at a different resolution, but you should see when you do playlist, the videos organized by date. Yeah? You weren't getting that? Okay. Yeah, I put everything up on YouTube. So if you go back,
On the old one, I was looking and for I think it was January 28th or something. There's only one video. Is that right? Or is one?
for our class, no, maybe there might have been just one. Oh, you mean there's only one video in the playlist?
For the 30th.
Yeah, there might have.
Second half.
Did it seem like it was missing something?
Yeah, it started at half the time.
Okay, there might have been. Well, January 28th?
30th.
Yeah, I might be missing it. Yeah. Yeah, if you notice that, let me know and I'll go look. I pushed up 100 videos up to YouTube. And so I might have missed one or two. But if you don't want this, what I think's easier is if you just go to YouTube and you look up Robert Math Guy, then this is my channel. And then you can bring up playlists. And then in the playlist, you can look up, you know, even my 0303 class. I mean, not like you would need it, but, you know, it's a little easier, I think, to navigate from YouTube than it is to navigate from Canvas. So, yeah, and if you want to subscribe, you can. I already have 10 subscribers, 82 views, and I've been messing with Photoshop, as you can see. I just got Photoshop the other day, so I'm like trying to learn all these things from it. All right, I think I'm done. Yeah, that answered everything. All right, let's get down to business. What we finished with last time was the idea. Yes, yeah. I'll address it because it's related to what we're doing today. That's fine. Yes.
I went through and started doing it, and I was going like a rock star until I realized I don't like there was like it was multiplication. You couldn't do that n plus 1 over 2.
Mm-hmm.
It didn't seem like I don't know. It was better than mine.
Well,
I couldn't figure it out after I plugged in my formula inside of like sine of whatever I came up with. You know what I'm saying?
yes. Watch. On the instructions here, it said, let's see. It says, using f of x equals x sine x, find a formula which represents the area under the curve. Okay, I want the formula consisting of a limit and summation. Do not try and compute the area. I just want the formula. So all I wanted, this one was supposed to be very straightforward, meaning it was supposed to be, I can even show you. Yeah, this is, if someone gives me any function, okay, it doesn't have to be this. Okay, and forget the interval, just put AB, right? Then I gave you last class, at the very end of class, this formula right here, in blue. Right there. See this? This is the area under a function on an interval. This sum. So all you had to do was replace the function here with x sine x. So it would have, and that would have been it. That's all I would have been looking for. So I would have wanted something like limit n goes to infinity, sum k equals 1 to n of x sine x, but x isn't x here. It's a plus, which turns out to be 1. No, wait. Was that the right interval? Or it was 0 to pi over 2. Sorry about that. So it'd be like a is 0 plus k pi over 2. And you kind of get that?
Yeah, no, I got it. I wrote that down. I thought that I don't know why I think all right.
Okay. Yeah. But in the future, if you have a question, just get in touch with me. I have no problem helping you out. Actually, that's it right there. That's the solution. What's that? Well, it's due right now. Yeah. So I mean, we can talk about anything you want after class, but I mean, it's due right now. Okay. So in the future, don't tear your brain apart. Just text me, call me, whatever. Just say, hey, I'm unclear on this or something. I will put them under files for the class. I will post the solutions. And normally I will do that, usually the day that it's turned in. That's another reason why I don't accept late quizzes, because, I want to get the solutions out to the class. So if I'm waiting on one person to turn in something late, then everyone's waiting on the answers, All right. Let's do it. So we ended with the idea of the sum, right? The infinite sum. And now what we're going to do is we're going to turn to the easier part, where we're no longer going to have the sum. We're going to use the fundamental theorem of calculus. That's kind of what we hinted to at the end of class last time. So I'm working in the book in chapter 5. And I'm kind of blending a couple of sections together here. It's like 5.2 with 5.3 and a little bit of 5.4. So I don't really know what I should call this other than definite integrals. All right, that's what I'm going to call it. Definite integrals. So we said last time, and I hate to write all this down again, that if somebody gives us a function, then the area under this curve, right, the area, I'll call it capital A, is equal to the limit as n goes to infinity. And again, this is all written down somewhere, so you don't have to copy it if you don't want, but everyone should know that this is the formula I'm referring to. That's it right there. Right? And this meant, like geometrically, what were all the f of a plus k times b minus a over n? Geometrically, in this picture with the area, do you remember what the f part was? Okay, which one was it? The base or the height of the rectangles? That was the height, right? So this was the height of the rectangle. So if you took like an arbitrary rectangle in here, right? If you took that arbitrary rectangle, the height of it is that one part right there, h. And then this part right here is like your w, your width. So you're taking a bunch of heights and widths, multiplying them, which gives you an area. And then the sum does what? This sum right here, it adds, right? It adds n of them together, right? N rectangles. And then what does the limit do? Infinite rectangles. So I just want you to make sure you understand all the aspects of the formula. You have the heights, the widths multiplied, that gives you areas. You add up all the areas. How many of them? N. Okay, let n go to infinity. You get the area. Right? That's what's happening here. So we're going to talk now about antiderivatives, and then we make that connection that we made last class of how the area is connected to the antiderivative. So before I can proceed with definite integral, we have to talk about antiderivative. And this is probably an overlap from Cal 1. The antiderivative says that we will call capital F, that's a function, an antiderivative of little f if the derivative of capital F equals little f. That's it. That's the definition for antiderivative. Some examples. Do we agree capital F of x equals x cubed? Little f of x equals 3x squared. Do we agree here that capital F is the antiderivative, or is an antiderivative of little f? Yes, because if I take the derivative of big F, I get little f, right? You can just check it. Derivative here, 3x squared. and that is this, check, so it's an antiderivative. But it's not the only one, right? We have actually a couple of possibilities. Let me try this. Capital F of x equals x cubed plus 10. Take the derivative of that. What do we get? Okay, 3x squared again. So the idea is that you can actually have two capital F's that are different that give you the same little f when you take the derivative. But they all have to have the same format. What would they all have to be if you wanted them all to give you a derivative of 3x squared? It would have to be capital F of x would have to be x cubed plus some constant, right? As long as that c is a constant, then when you take the derivative, it'll go to 0. All right, that's the basic idea. I know a lot of you have seen this, so I'm not going to beat this to death. Let me get a new page here. The general antiderivative of little f is a capital F of x plus any constant. I'm just writing down what I just said. So if you take some little function, take little f, you find any antiderivative and then add c to it, that's going to be the general antiderivative. Now, recall from Cal 1, the power rule. Do you remember the power rule? Yes, you do, because we just took a derivative and you used it, right? Power rule said this. If I'm trying to take the derivative, or is everyone comfortable with the prime notation for derivative? Is that okay? Okay, if I'm taking derivative of x to a power, it'll be power x to the n minus 1, right? That was it? Okay, that's the power rule for derivatives. For derivatives. What we'd like to do is we'd like to come up with a rule that would take us backwards. Again, starting with x to the n, but go backwards to find its antiderivative. So we have what's called the power rule for antiderivatives. Power rule for antiderivatives. So here's what it says. If little f of x equals x to the n, then the general antiderivative will be equal to, so when we start out with the x to a power and we go backwards, the power is going to have to do what? It's going to have to go up by 1, right? So let me put that here. But the problem is, right now, if I look at the right and I take the derivative, right? If I take derivative of x to the n plus 1, the n plus 1 comes out, doesn't it? That power comes out. And over here on this one, there is no n plus 1 in front. So what we want to do is eliminate that n plus 1. So all we have to do that is put a 1 over n plus 1 in front of this. Now we do have a condition here. N cannot be negative 1. If n is negative 1, this won't work. Because if n is negative 1, don't you get division by 0 here? Okay. We'll deal with that in a second, though. We'll have an answer for it. So let's try and do this rule a couple of times. Find capital F if little f of x equals square root x. All right, so what I'm going to do is I'm going to use this rule, right? But I'm going to first rewrite Square root of x is x to what power? 1/2, okay? And then, that's my n, right? That's my n. So add 1 to it. What's 1/2 plus 1? 3/2. So my capital F, my capital F of x should be 1 plus n 1/2 plus 1 x to the n 1/2 plus 1. So I'm going a little slow there, just putting everything in there, right? All my n's. So here's my n, 1 over n plus 1, x to the n plus 1. Everyone, I forgot something in here. What did I forget? My plus c. Go back up to my formula. Go up to the formula up there. I forgot to put my plus c up here. Do y'all see it? Right there? Plus c. You need a plus c in here. So plus a constant. Because we're finding the general antiderivative. So we'll just get used to always adding on this c. What now? Add them up. So we've got 1 over 3/2 x to the 3/2. And 1 divided by 3/2 is really 2/3, just reciprocal. So plus c equals 2/3 x to the 3/2 plus c. And you can always check it by taking the derivative, right? If I take the derivative of that, I should get back the square root of x. Okay, show of hands. How many of you have seen the power rule for antiderivatives? So a good number of you. All right, some of you haven't. That's okay. I'm assuming you haven't. All right, so I'm going to keep on asking you to find antiderivatives, right? I'm going to keep on doing that. So I need a cleaner way of actually asking you. So I'm going to introduce some new notation now. So instead of me writing down like find capital F of x, given little f of x is this, we have new notation. So I'm starting a new page here. Integral sign and notation. So this is the way I was doing it, okay? This is the old way. I was just writing down find, bless you, capital F of x if little f of x equals, blah, blah, blah. That's what I was doing, right? I was saying find the antiderivative if the little f is this. So instead of doing that, here's what I'm going to write. Okay, that's the integral sign. It's a stretched out s, little f, and then we put dx behind it. And let me label some things here. Like I said, this is called your integral sign. The f of x in here is called the integrand. And the dx here is called the differential. Now, at this point, when you're first introduced to the integral sign and integral notation, if you are not shown all those rectangles added up, like we were doing last class, right? If you were never shown that, you would really have no idea like why they're using this. But now that you've had the exposure to the rectangles, you can kind of see, and I've already alluded to this last class, this right here is really just the what? That's like the sum, right? This right here is the what? F of x? That's the height of your function, right? The dx is really like the width, right? That's like remember we were using delta x? Dx is like the delta x. So do you see how the integral sign really means add up forever, or add up an infinite number of heights times widths? That's what it is, okay? You there? Yeah. Now, we're going to act like we don't know that, and someone's just introducing this notation, but now you know why they're using this notation. This symbol means something, and what's inside means something. Okay. I guess I could have left it, but So this means find the antiderivative. So this means find a capital F of x plus a constant. Find it. So new notation, we'll do a couple of examples. As an example, if I write 1 over the fifth root of x dx. So what I'm saying is, give me the general antiderivative of 1 over the fifth root of x. Now, the only thing that we're going to act like we know at this point is the power rule. So the only way the power rule will work is if you have the power of x. Do you have the power of x here? What is it? Okay, so I'm going to leave it as 1/5 on the bottom first, then I'll bring it up. So fifth root means the 1/5 power. Is everyone comfortable with that? And then power rule, you can't have the power down in the denominator, you have to have it up in the numerator. So we bring that up. It's x to the negative 1/5 dx. That okay? Okay, that's your x to your power, right? Now we're ready? That's your n right there. So the answer to this should be 1 over n, negative 1/5, plus 1, x to the negative 1/5 plus 1, plus some constant. And, you know, hopefully with time you get faster and faster with this stuff. The fractions, you just kind of see them. What's negative 1/5 plus 1? 4 over 5. And then what's 1 over 4 over 5? 5 over 4. So 5/4. X to the, we already said this would be 4 over 5 plus c. That's it. Questions? All right? Now, a few properties that we should know with the integral sign as we move ahead. Properties. What do you think this property is going to say? If you have a constant in front of a function inside the integrand, what can you do with the constant? Pull it out. Okay. So your constant can come outside the integral. Okay, so that's one property. Here's another property. If you have the integral of some function plus or minus some other function, you should be able to separate it into two integrals. Right? Does everyone see that inside here, the integrand, what's in yellow here, the integrand is the sum of two functions. So the property says that if you have that, you can break it into one of the functions, the integral of one of the functions, plus or minus the integral of the other function. And that's pretty straightforward because with derivatives, it's the same way, wasn't it? With a derivative, if you had two things you want to take derivative, you do derivative each one. So it works the same way with the antiderivatives. Now, I'm going to write this in red because this is wrong, but I'm showing you that it's wrong, okay? The integral of f of x times g of x dx does not equal the integral f of x dx times the integral g of x dx. Why do you think it does not work that way? Yeah, how is products with derivatives? I mean, remember with product rule in Cal 1, when you had two things you wanted to multiply them and take the derivative, it wasn't just derivative of each and then multiply. It was what? F prime G plus G prime F, all that, right? And then quotient rule was a big freaking mess when we got to multiplication division, right? Same thing with antiderivatives. You cannot just take the integral of a product and split it into two integrals multiplied. Now, I did have one student ask me a question on the quiz over the holiday that I'd like to share with you. And I'll bring that back up. We were looking at this. Let's just look at that. If we had that, the sum of x times sine x, do you think you can do this? No, you can't. You can't split a product into... The sum of two products is not the same as the product of the two sums. Do you believe that's true? Do you believe that's true? Do we care? We could show a counterexample. Okay, I could show you an example where you could easily compute one and show it's not the other. But we'll take it, I guess, on faith for this. But just keep in mind that that's also tied into this, right? If the integrals are just sums, then this should be the same. The integral of a product is not the product of the integrals. If it were, Cal 2 would be a lot easier, and Cal 1 would have been a lot easier because derivative of product, no, there wouldn't be product rule. Okay, so now using those properties, let's do a couple more examples. Let's find antiderivative. Now I'm going to give you several things. 3 over x to the fourth minus pi over the third root of x squared minus 5 over x. Now, you can split this into 3 separate integrals, can't you? Because there are 3 terms. But normally, we don't, because it's just more writing for us. But what we can do is focus all of our attention on each one of them separately. Like when we actually do the rule, we'll do it on each one. So I'm going to leave it written like this, and just keeping in mind I can find the antiderivative of each of them separate. So let's rewrite some stuff. That first one can be rewritten as 3x to the what? Negative 4. Okay, minus, what about the next one? Pi x to the negative 2/3. So that's the, on the bottom, right? The cube root of x squared is 2/3. But then bring it up is negative 2/3. Is that all right? And then the last one. Negative 5x to the negative 1 dx. Any questions on where I got any of those numbers or anything like that? Now keep in mind what I'm actually doing, I'm going to do 3 integrals, but I'm not going to write all the integral signs, right? You got a question? Come on. Oh, yeah, exactly. That's why I put it there. Yeah. That's why I put it there. Okay, so let's try this. Let's look at the first one here. Okay, I'm going to take the antiderivative of that. The 3 in front is a constant, right? So I'm just going to ignore it, which means that it's going to come down as part of my answer. Notice there's no more integral sign here. 3 times. Now, what's the antiderivative of x to the negative 4? 1 over, I'm going with some detail here. Negative 4 plus 1, x to the negative 4 plus 1, right? That's the antiderivative there. So that's just this part right there, right? Now the next one. The minus pi is out in front. See, I just threw the pi in there just for fun, right? Just to see if it would confuse us or not. Times 1 over negative 2/3 plus 1, x to the negative 2/3 plus 1. Again, no integral sign anymore, right? I'm done. Like I'm taking the antiderivative. So that's this piece here. Questions there? Now, if you follow the formula, it's negative 5, right? But then times 1 over negative 1 plus 1, x to negative 1 plus 1. That's a problem, isn't it?
Yes.
That's a problem because we said this formula doesn't work with negative 1. And you can see it. We get the division by 0 there. So basically, we need to kind of like look at this in a second and figure out what the heck that is. But we'll get to it, okay? Right now, I'm just like, uh-oh. Let me clean up the first two. What is that negative 4 plus 1 on the bottom become? Negative 3, but then you have a 3 in front. So cancels out. You just get negative 1. So negative x to the negative 3. What does the negative 2/3 plus 1 become? 1/3, but then 1 over 1/3 is really 3. But then you have the negative pi in front. So negative 3 pi x to the 1/3. Now the last one I wasn't sure about, right? So I'm going to rewrite it, but watch the way I write it. Negative 5 integral of 1 over x dx. So what I've done there is I took the negative 5 out, right? I took the negative 5 out, and I put the integral sign back in because I'm saying I haven't taken the antiderivative of that one yet, right? And I went back to the original form. This was the original form of it, right? And I wrote it that way in hopes that you would remember that 1 over x is the derivative of something, natural log of x. So we have to remember that the antiderivative then of 1 over x would be natural log of the absolute value of x. And I'll write that down after we do this exam, finish this up. Negative 1 over x cubed minus 3 pi cube root of x minus 5 natural log absolute value x. And then at the end of it all, a plus c. Yes.
I guess
Why is it the absolute value, or why is it natural log? Because natural log is not defined for negative numbers, right? So that just makes it at least non-negative. You still can't plug 0 in there, right? So that's the only thing. That's the only reason. All right, now I'm going to put something up here, the power rule again. What we had was, I'd written it down earlier a certain way, right? But now I'm going to use our new notation. The antiderivative of x to the n dx is equal to, there's two possibilities. It's 1 over n plus 1, x to the n plus 1, if n is not equal to negative 1, plus c. So it's saying that the antiderivative of x to the n is just the power rule, right? As long as the n there is not negative 1. Now, if it is negative 1, then what is the antiderivative? Natural log of absolute value of x. So that takes care of both possibilities. Well, takes care of if n is negative 1, I forgot my negative 1, or if it is not negative 1.
Can you rewrite the L to select the direction of
Can you do what?
the L?
You want me to rewrite my L?
Yeah.
You want me to do a different L? Well, no. That's the way I've always written my L. I'll give you a bigger absolute value. How about that? Okay. A lot of my college algebra students still think that ln is in. So they're always like, okay, I hit in on my calculator. I'm like, okay. I understand. It does look like in. All right, now there are a bunch of other functions that we should know the antiderivative of, just from our experience in Cal 1. So let's look at some common antiderivatives. This will be common antiderivatives. So these are ones that I think you should just know. Kind of like if I said, hey, what's the derivative of sine x? Everyone's like cosine x, right? So it should be the same way for these, for antiderivative. The antiderivative of e to the x dx is itself, right? Plus c. That makes sense, right? The derivative of e to the x is e to the x, so the antiderivative of e to the x is e to the x. All right, what's the antiderivative of cosine x? Careful. Just sine x plus c. The antiderivative. The derivative of cosine x is negative sine x. But the antiderivative of cosine x, so you're saying, you know, where does cosine x come from? It's the derivative of what? It's the derivative of sine, right? Now, what's the antiderivative of sine x? That's negative cosine x. Plus c. I'm not a huge, like, I'm going to nail you for not having plus c, but some instructors are very, I mean, they'll take the whole thing off if you forget c. I'm not, but I want you to try and remember to put your c in there, okay? Okay, so those are common ones. We can't really go a whole lot further without getting kind of messed up. I mean, even if we try and do tangent, the antiderivative of tangent. Well, the derivative of tangent is secant squared, right? So we do know that. We do know that the antiderivative of secant squared x is tangent because that's where it comes from, right? But what I'm saying is, what's the antiderivative of tangent x? So you have, I'll tell you what it is. It's, well, it's not even on this formula sheet here. I included in the class on our, let me get to it real quick. Remember I said we have a formula sheet that everyone's allowed to use on the test? See if I can get back in here without logging in. So under our files for our class, there is, let's see, formulas. Where are they? Formula sheets. I'm going to go ahead and open this for us so we can all take a look at it. There's multiple pages of formulas here. There's, you know, algebra, there's trig, special function. Here's the rules of differentiation. Here's what is called the table of integrals. So I want you to look at number 2. Can you all see 2? It's kind of hard to make it out here. Number 2. Number 2 is basically power rule, but using u's instead of x's. So the antiderivative of u to the n, du instead of dx, is, now what is this? It's the 1 over n plus 1, but they slid the n plus 1 underneath the x. So it's the same thing. And then plus c, as long as n's not equal to 1. And then look at this one. What is this? Yeah, this is 1 over u. So this is if n is negative 1. And then here's the e to the u. Here's a to the u. We didn't talk about that one. Here's sine u. Here's cosine u. Here's secant squared. But then there's a bunch of formulas. Okay? You're allowed to have all these on your test. But that also means that I could give you something that looks like one of these, and you need to be able to apply the formula. So I would maybe take a little bit of time to go through this formula sheet and see what's there. Okay, there's tangent. Okay, what's the antiderivative of tangent of x? It would be a natural log of the absolute value of secant x plus c. Right? So there's a bunch there. Be aware of that. That's actually, those are the only 20 formulas you're allowed to have, though. You're not allowed to have any others. I think the book has more. Oh, yeah. The back of the book, it has the differentiation table, right? And I'd make you stop it at 20, but the back of the book actually goes and has 120 formulas for integration, for antiderivatives. And you could probably find somewhere a book this size of table of antiderivatives. Or you just type in Wolfram alpha, and then you have even more than that, right? But just be aware, that's all you're allowed to have on the test. So right now, according to me, if I gave you a problem like this would be fair game. You know, if I gave you, as an example right now, you know, what's the antiderivative of secant x dx? If that was a quiz beginning of next class, then you better have that formula sheet printed out because you're allowed to have it, right? So I would have that next class, and then hopefully that's on there. Is secant on there? Is the antiderivative of secant on here? Yes. It is natural log of secant x plus tangent x, absolute value plus c. That's the antiderivative. Now we are going to spend some time later on figuring out why these formulas are true. Okay? We're not just going to get them and just hand them to you here they are. But at this point in time, you should know we should start working with them. We'll prove why that's true in a second. I mean, not a second, later as the class goes on. Let's look at this one, though. Look at that one that was tangent. Told you it was on here. The antiderivative of tangent x dx, according to what the formula sheet says, is natural log of the absolute value of secant x plus c. Right? Let's just check that that's true. How could we check that that's true? Take the derivative of the right side. And what should it give us? The integrand. So let's start with natural log, absolute value, secant x. Take the derivative. So let's practice, it's been a while, chain rule. What's the derivative of natural log of something? 1 over the something, right? The secant x? But then chain rule says now go inside the natural log because you've already done the derivative of natural log. What's derivative of secant x? Secant x tangent x, right? Isn't it? And then what happens? Secants cancel and you're left with tangent x. So it is indeed the antiderivative. Yes? Y'all see that? This is what's going to make calculus 2 difficult, is the fact that, yeah, you can see that that obviously turns into tangent x when you take derivative. But how do you get from tangent to that? How do you go backwards? Right? Imagine, you're starting with tangent, right? how do you know right now to go, oh, tangent is actually 1 over secant x times secant x tangent x? How do I know to do that? And then to say, oh, I realize that this is the derivative, right? That's the derivative of natural log of something. And then this is the derivative of what's in there. I mean, you see that it's much more difficult to kind of reverse engineer this stuff. And that's what this class is about. So we're going to have what are called the techniques of integration, which basically means the techniques for finding antiderivatives. And they're going to be substitution, integration by parts, partial fraction decomposition, trig substitution, trig integrals. I mean, there's like 6 different techniques. And we'll spend a day or 2 on each one. Okay, so for now, though, everyone understands you should have your formula sheet. Any of those are fair game? Okay. Can I proceed then, or you want me to give you another example? What do you want? You good? All right. So now we're going to get to what's called the evaluation theorem. Oh, you know what? Hold on. Don't write that down yet. The process of finding antiderivatives is called, well, in Cal 1, the process of taking a derivative was called differentiation, right? Differentiation. Okay. In Cal 2, the process of finding antiderivatives is called integration. Integration is the process of finding an antiderivative. Integration. This right here, when we went back to that, we called that the integral sign, right? Integral sign. That's why it's part of that word, integration, integral. So that we're just trying to get some language as you hear me talking up here. You know, okay, we're going to be doing some integration now. Okay, that's what we're talking about. Now, thus far, this means find the antiderivative, right? Find the antiderivative. But now we introduce something new called the definite integral. Now, if this is called the definite integral, what I'm about to put up here, what's up there is going to be called something else, and I'll put it up there after I explain what the definite integral is. Okay, the definite integral is going to look like this. Same thing, right? With 2 additional things added, A and B here. The A and B are called, the A is called your lower limit of integration. And the B here would be called your upper limit of integration. What we're getting to now is the idea of the area. Because remember the area, we had to have an interval? Okay? This definite integral is going to basically produce that answer for us. But we need the 2 endpoints. So that's what we do. We write them as on the bottom and the top of that sum sign. Now the definite integral is connected to the area. So I'm going to just draw it real quick. If we take a function like this, f, we go from A to B, then the area right here is equal to the definite integral. And this is a result of the fundamental theorem of calculus, which I'm not going to get into a lot of detail with. You know, I know that there are some instructors that get really deep into proving, you know, the fundamental theorem of calculus. I'm not, because I figure if you ever need to know the proof, then you're probably a math major and you're going to prove it a completely different way than the way that they would do it in this book. So you'll get there eventually if you're a math major. Don't worry about it. Take it on faith for now. All right? So this area is that, but we said already, hey, that sum was just, you know, our sum and then all our little heights and widths. So it kind of makes sense, hopefully, for us. The A and the B just give us the endpoints. So if this right here gives us an answer, right? It's usually a number, isn't it? Right? That's usually a number. I'm going to put usually. It's not always. Okay? Usually I get a number. Then that kind of makes sense that we would call it the definite integral, because definite means we have a definite answer, right? Like a definite numerical answer. As opposed to up here with this, where all we got with this, without the A and B on it, was what? Just like a function plus C, right? But it wasn't a number. So we call this one up here, not the definite integral, the indefinite integral. It kind of, you see why it doesn't make sense for me to first show you that and say, hey, we call it the indefinite integral, and then, you know, you'd be like, why? But I think it makes more sense to say, hey, this one gives you a number, it's a definite answer now. The other one doesn't give you a number, right? So we need to make sure we understand that language. If we're ever studying definite integrals, we're studying things that give us numerical answers. If we study things that are indefinite integrals, we're going to have functions plus C, exactly. All right, so I'm going to box this. This is a pretty big thing right here. Well, I don't need that. I don't need that either. Just that. That right there is our Big Daddy result. So let's see how we can apply this to an example. Find area under f of x equals x squared on 1, 5. You may recognize this.
Yeah.
You recognize this? Yeah, second class, right? Yeah, exactly. I think it was 41. Well, let's see what it is, okay? Now, I do want us to remember that you may or may not remember the suffering we went through, okay? Where was it? Is it all this? I think this is it right here. There it is. Yeah, 41.33. Right? Do you remember all this? First time you ever saw this, it was like, what the hell? Okay. And we got all the way to that 41.33. And then right after that, I showed you, hey, check this out. See if this is x squared, and we know the antiderivative, it's just plugging in the endpoints, and we get the same answer. Okay, we're there now officially. So let's do this. But watch how things are a little different. The way that we write things is going to be different. So whenever we see this, find the area under this function, the first thing I know is I'm needing an integral, right? Integral sign. Now, what are my limits of integration? 1 and 5. What is the integrand, the thing we're integrating? X squared. And you always put the dx. Now the dx, let's not let this distract us right now. Right now, just look at it as like just imaginary placeholder. It's almost like a 1 sitting there. Just sitting there right now. It's always going to be that until we start to get into more advanced problems. Then the dx will have to mean something. For now, just look at it as a 1. So let me even erase that. I don't want that highlighted. All right, so what I'd like to do now is I'd like to find the antiderivative, right? So that's what I'm going to write next. What is the antiderivative of x squared? X cubed over 3 or 1/3 x cubed, however you prefer it, right? Now, I usually, in the past, I would put plus c. If this was a what kind of integral? Indefinite, right? But this is a definite integral. With definite integrals, we do not put plus c. All you do here is you draw a line. I'm going to do it a different color because I don't want you to confuse it with like a number or a letter. It's just a line. This is standard notation in calculus. And at the bottom of the line, we put the 1, and at the top, we put the 5. And what this greenish line means is that we are going to take this antiderivative, and we are going to evaluate it at the 5 and the 1. All right? At the 5 and the 1, we're going to evaluate that antiderivative. So now, I'm going to take the 5 first and plug it in to my x, into the antiderivative. So you get 1/3 times 5 cubed, right? Then you will always now subtract from this what you get when you plug 1 in. So 1/3, 1 cubed. Which is, we did this before, right? 125 over 3 minus 1/3, which is 124 over 3, which is the same answer we got before. Yes? Okay. Yes. Exponent. A to the what? A squared plus b squared. Wait, a squared plus, is that what you're saying? You can't combine those. No. If it's addition, you can't. Yeah. If it was multiplication, you could. But all you could do then is go ab squared. Now, this notation I showed you here in the first example, I want to get it written in general because normally, you show it to the student in general first, then you do an example, but I like to do an example first, then show you the general. So here's the general layout. In general, if we have the area, if we want the area under f on a closed interval AB, it'll be equal to the integral from a to b of little f of x dx. Right, that's the way we write that. But the antiderivative of little f is what? We don't know, but we've called it big F of x, right? Then we put in here that line AB, which really means what? First plug b into big F, right? And then subtract from that a plugged into big F. That's what we just did, isn't it? We found the antiderivative, big F, which for us was 1/3 x cubed. Then we plugged the 5 in, which is capital F of b. Then we subtracted, plugged the 1 in, and then we got the answer, right? Okay. That's a lot better than doing the limit as n goes to infinity of the sum k equals 1 to n of f of a plus k times b minus a over n, all that, right? Way better than that. And faster. Now, there are some subtle things we need to be careful with here. Find the area under f of x equals cosine x on the interval 0 to pi. So what is the integral that we would set up here?
Sin x
Integral
from 0 to 2 pi.
from 0 to 2 pi, right?
Cosine of x.
Cosine x dx. Everyone agree with that? Now you have to ask yourself, what's the antiderivative of cosine? Sine x. And I'm going to evaluate that at 0 and 2 pi. First, I do which one? The 2 pi. Now, here's the way I like to do this because we're going to be doing this a lot. I like to draw two sets of parentheses with the minus sign between them because later on things get complicated and signs get mixed up and stuff. Look, you're going to have what you get when you plug in 2 pi, and you're going to have what you get when you plug in 0, and then you're going to subtract them. So I keep them nice and separated right now. This one, though, sine of 2 pi, that's not going to be too tough. The other one's sine of 0, not too tough. Well, what is sine of 2 pi? 0 minus what's sine of 0? 0. So your answer is 0. 0. Do we mess up? Does that make sense? Look at cosine, right? Take a look at the cosine function. What does cosine look like between 0 and 2 pi? Starts up here, right? Comes down through here, bottoms out, comes back up here, right? Goes like this. Something like that. That's cosine. Well, the area here isn't 0. And the area here isn't 0. And the area down here isn't 0. So why is our answer 0? That's right, which doesn't make sense, right? I mean, area shouldn't be positive and negative, right? Area is area? Yes. That's right, they cancel. The bottom, but why is it counting? I mean, area is area, right? I mean, when do we ever have negative area? You know what I'm saying? Like if I measure length times width, or width times height, the width should be a positive number, right? And the height should be a positive number. So when you multiply those two, you should get a positive number. The problem is that our height of our rectangle was based on the function's value, wasn't it? It was f of whatever. And when we get to the greenish part on the bottom, isn't our function's value negative because it's below the x-axis? So it's counting that multiplication, that little rectangle, as a negative number. So what's happening is it's canceling. Yes? Mm-hmm. Mm-hmm. Exactly. This would have been like they were walking and then started walking backward. Yep. So they're net, but that would be a linear, we'd be having to talk about a linear motion. You're walking certain speed, this direction, that's positive speed, and then you start walking the other direction, backwards. So your net displacement would be 0. But we don't like that, do we? I mean, we don't like the idea that we get a 0 here because there is an area, right? What would make more sense is to tell me what's the net area. So how could you figure out the net area? You could add them, but what do you mean by them? Like sine of 2. Geometrically, what we really need to do is find the area between 0 and that first spot, and then the area from that first x-intercept to the second x-intercept, and then the area from the second intercept to the end of our interval, right? It looks like a circle. It's not, though. That's not it.
So only the positive parts of sine in the circle?
Let's see what happens. Let's see what happens.
Do you think the origin, if we lowered it, would that make a difference, or would it still be 0? Like instead of starting from 1 up there, you start from
Good question. If you took the whole function and moved it down so it was all negative or all positive, Let's move it up. I think you want to move it up? Okay. I think the question is, if we shift the entire function up 1, then it'll do this instead. Right? Now, if I look for that area, will that give me the area that I'm really looking for? Because what I really want is the net area, all those together. So would this give it to us? Look what this would give us. This would give us everything underneath the function. Is that the same as what's up there? Look at, we have like hard corners here. We don't even have, you see what I'm, man, I'm going to like yank this thing out of the wall. What do you think? Do y'all think that this area on the bottom here, all this in here, do you think that's the same as these together? You would have to convince me that that's true. I don't think it is. It's not. But you could actually even check it by looking and saying that this function isn't the same as that function, so therefore evaluating at 2 different endpoints should give you 2 different answers. Okay, let's do this. That's a good thought. I mean, I don't think that's ever come across my mind to try that, but I don't think it'll work in general. Yeah, why don't we go from 0 to pi over 2 of, what was it, cosine x dx? That would give us just this. I'll just call this a, right? That will give us a, right? This right here is a. And then, now this is somewhat symmetric. Do you agree? Like we have, whatever a is, that one over there is the same. And these two down here are double whatever a is. That's because of symmetry, though. In general, if this were some weird polynomial function, we would have to go and set up multiple integrals, which is the way I'm going to handle this one. I'm going to act like it's not symmetric. So what is the antiderivative here? We already said it's sine x. Evaluate 0 to pi over 2. Now 2 little endpoints here. Sine of pi over 2, 1. Sine of 0, 0. So we get 1, don't we? Does everyone agree with that? Anyone have a question on that? What is my next integral going to be? We'll call this b, right here, this b one. Integral where? Pi over 2 to 3 pi over 2 of cosine x dx. Again, it's the same antiderivative, isn't it? But just 2 different evaluation points. Any questions? Sine 3 pi over 2 minus sine of pi over 2. So this is sine of 3 pi over 2 is negative 1, right? But then minus sine of pi over 2 is 1. So negative 1 take away 1 is negative 2. But that's because it's below the x-axis. So if we wanted to truly count that as area, it would be a 1. I mean, sorry, a 1. It would be a 2, right? So we take the absolute value of it, it would be 2. And then do the last one, part C, and you would get what? 1. So the total area would be 4. If we looked at it as absolute value, the net area. The net area. So the way to do, if someone asks you for net area, then what you want to do is what? Look at your endpoints, right? And then look at your function in there and find the what? The area, but how are you going to find out what your sections are? You're going to need your x-intercepts. And then you're going to have to determine at each x-intercept in between them whether or not your function is above or below. But you'll be able to tell that by the answer. If the answer is negative, you'll know it's below. If it was positive, it's above. Does this make sense or not? No? Let's try something and at least a setup on it. How about find net area under f of x equals, hold on, x cubed minus x squared on the interval 0, 4. You know, switch this x right here squared, just make it an x. So I'm going to go off this without even having a picture. I'm just going to try this, okay? If you just attack this as is right now, integral, 0 to 4, right, of x cubed minus x dx, what is the antiderivative of x cubed? 1/4 x to the 4th minus, what's the antiderivative of x? 1/2 x squared. And I'm going to evaluate this from where to where? 0 to 4. Everyone following this? That equals, now I have two things. First, plug in 4. What's 4 to the 4th? Divided by 4. 64? 4. It's basically 4 cubed, 64. So 64, take away 4 squared, 16 divided by 2, 8, right? And then zeros in there is just zeros, right? So you get 56. Now, that's what you think the answer is, right? But that's not going to be all the areas considered to be positive. That's just going to be, if there was some area positive, some negative, it's adding the negative, subtracting the negative from the positive, and that's what you're getting overall, right? So why don't we try and take a look at the graph? What's that? Whatever the integral is from endpoint to endpoint, right? Positive or negative. That's the integral. That's what the integral gives you. Okay? What we want when you want to specify that you want just the positive, you have to somehow say that in the question, which is what I've said here. I would state it in the question. But how would you know where to find the negative parts? Okay? So let's try it. You take the function, you find the x-intercepts first. So take, what is it, x cubed minus x, set it equal to 0? Right? And factor out an x. Factor difference of squares. And you get 0, 1, and negative 1. So what I know is in my graph, I have an x-intercept at 0 and at 1. And then 4 is my endpoint, right? 0 is my endpoint, and negative 1's on the other side, so I don't even need to care about negative 1, do I? Negative 1's over here?
Oh, okay. Because 0 is the endpoint, right?
Yeah. That's right. 0 is the endpoint of my interval. So I'm only concerned with what's going on over here, right? Between 0 and 4. So you could, right now, set up this integral. Instead of going from 0 to 4, you could do what? 0 to 1 and then 1 to 4. And let's see if our answers, if any of these come out to be negative. 0 to 1 of the same function, which means it's the same antiderivative, but we're going 0 to 1 instead. And look what we get. What happens when we plug in 1? 1/4 minus a half, which is negative 1/4. And then over here, when we plug in 0, 0. So you actually did have some area there, didn't you? Negative 1/4 below the x-axis. Do y'all follow on that? Which means if you're looking at, total area, counting the bottom as area, then you don't want to count that as a negative 1/4. You want to count it as a 1/4. The absolute value. That's right. Now do it from 1 to 4, and you should get the rest. I'll try and squeeze it in here. Integral 1 to 4 x cubed minus x dx. Yeah, we already did it. We already did it at 4, right? And what did we get? 56. And then we do it at 1 and we get negative 1/4, right? So now it's 56 plus that, right? Plus another quarter. So it's actually, I'm going to go to a new page here in a second. But are there any questions on what I've done with that so far? I'll put the answers over here on the left side. That first integral, I had negative 1/4. The second integral, I have 56.25, right? And this other one was negative 0.25. So do you see that when we add the two together, we get 56, which was the answer from up here? But if we really wanted to know like the total area, counting bottom and top, the answer wouldn't be 56, it would be what? 56.5. Now, I want to make sure I use the same language that the book is using. Evaluation theorem, yeah. Yeah, no, they don't really talk too much about it. Net change. Net change. This, what we did up here is the net. Right there, the 56. That's net. Because net's your positive and negative put together, take away, add. It's your net. What happens at the end? This right here, you were saying gross. You could kind of look at it like a gross, but it's really more of like a, you would have to give it some quantity, like the displacement, right? So if you were to ask a person, if this were a person walking, right, the net displacement would be 56. But the total distance moved, total linear distance moved, would have been 56.5. That make sense? Okay. Yeah, it's just weird. It's a weird concept we haven't really dealt with. All right.
Do we combine those to scalar and vector quantities or not?
Combine.
Well, I mean, like the 56.5 is a scalar and the 56 is a vector quantity.
Elaborate more. I don't know
I'm
what.
trying to relate it to physics.
Okay.
As in, like, when you're talking about displacement in the distance,
Mm-hmm.
displacement is, and it's like from point A to point B.
Mm-hmm.
Distance is going to be the distance traveled, and the velocity is a vector
Well, see our vector here. See, this is all with talking about linear displacement. So our vector is, our speed vector is always just in one direction. It never changes direction. So it's basically our speed. Right? Because the vector is what? Magnitude and direction. But if your direction's always the same, then it's the same, it's just speed. So what you could look at, if it's like a spring moving, right? You know, the spring would be the easiest thing. If we went the integral from 0 to 4, it would be the spring moved and stopped. How far is it from the original point? Displacement. Whereas this other integral is your total distance the spring moved through all the oscillations. I think you get that. I don't think we can assign a vector to it, though.
Yeah, I was wondering.
Yeah, I'm trying to think of a way that we could, but if something else pops in my head, I'll. Oh, I wanted to show you the graph real quick of this. We only have 10 minutes. Huh? So it was x cubed minus x, right? And pen with 3. So there's the function right there. So I can't go out to 4, it's too big, but you can see that we had a little bit of area under here. But you see, we didn't need the graph to do that. That's the negative 0.25 right there. And then everything to the right of that, that was the 56.25. Get it? Now, we did that without a graph. But the key was we needed the x-intercept, right? And we needed to then break up our integral. And then anytime we saw negative, we said, we know it's below, right? Anytime it was positive, above. What would the, I'm trying to get you to think ahead here. Let me move this back here, zoom out. Where's my page down? Look at that graph there. Just thinking ahead here. See that graph? Got it? What do you think this might give us? So I'm going to draw a quick thing of that graph. Went up like this, came back down, went back up like that. What do you think this integral would give us? It was x cubed minus x dx. Just think about this idea. Negative infinity to infinity. 0. Think so? Let's see. This yellow little area here would cancel with that yellow area there, right? And then if you go out to the right, whatever this area is here should get canceled off by whatever area is over here, right? Because one of them is positive, one. So it's, it's like symmetric, and so it looks like it would be 0. Yes. That's a good conjecture that it should be. Well, if it's symmetric, we don't call this, symmetric over the origin. Correct. Yes. But it would have to be that. And there are a lot of functions that are. But if it did something a little different, if it were like an even function or odd, it won't necessarily. So we'll talk about some of the properties. But what I wanted you to see was, what about this idea of letting our endpoints not be A and B, but let them be infinite, right? Here's another one for you to consider. What if I took the function f of x equals 1 over x, and I asked you to look at the interval 1 to infinity. So at 1, what's my function's value? 1. What does this function do as I start going out? It gets closer to 0, doesn't it? And closer, and it never gets there, does it? It has what we call a horizontal asymptote. Now what I'm asking for is the area underneath that, right? from here all the way forever. What do you think? Infinite? Never does. Never stops. So you have area in there, right? I mean, that would be the idea, maybe, or maybe you don't think so. How many of you think it would be infinite?
Does this go back to when you were explaining E to the X?
This
Similar to that?
this goes back to when I was talking about kind of like the idea of adding things up forever. I don't know, and sometimes it doesn't do what you'd think it would do. Yeah, maybe the numbers would be so small they wouldn't be relevant. Okay, well, look, let's not argue about it. Let's figure it out. Okay, this isn't a very far extension from where we are right now. Setting up this integral, it goes from 1 to infinity, doesn't it? All right. And it's, what was it, 1 over x squared? dx? All right, that's the same as the integral from 1 to infinity of x to the negative 2 dx, right? Now use your power rule. So 1 over negative 2 plus 1 x to the plus 1 evaluated 1, 2. What's that?
Is this negative 1 over X? Is that what you're saying? And then you plug in the number.
It's going to be negative 1 over x. Yes. The antiderivative, is that what you're saying? This? Yes. I'm just showing all the detail. Do y'all see that, though? Okay, let me clean this up. Also, just keep in mind, I've got infinity in here. Infinity is not a number, right? Infinity is an idea. So let's just keep that idea in there. This turns out to be negative 1 over x, 1 to infinity. You can't plug infinity in, but you can think about what happens. So yeah, it's like a limit. What would happen right now? What I'm trying to do is the top one right here. What would happen if I let x become infinite here? You get negative 1 over infinity, which goes to 0, doesn't it? So what's happening here is that this is headed towards something minus something, right? The first one is headed towards where? We just said 0, right? Where's the second one headed towards? Plug 1 in, negative 1. And so what you get is what? 1. So what turns out happening here is that area is finite. It is not infinite. This problem right here, that area is finite. Now, watch this. If I change the function, that was 1 over x squared, right? Watch, if I change that function to 1 over x, and I look at it on the same interval, it behaves pretty much the same, doesn't it? It starts out at 1. It starts dropping down towards 0 as I go out, right? But look at what happens in the integration. 1 over x dx. What's the antiderivative of 1 over x? Natural log x. And where am I going to evaluate that? Now, I'm not going to put the absolute value around the natural log all the time. Okay? Here I didn't. Why? Because my interval is 1 to infinity. So x's are positive, so I don't have to worry about it. Okay, 1 to infinity here. So plug in infinity. What does the natural log function do as you go out to infinity? So you have to know what natural log looks like. It goes like this, doesn't it? Natural log goes like this. Don't forget what natural log looks like. I'm going to throw it in right here. Here's what natural log of x looks like. Yeah, so it goes out and it's growing. It grows kind of slow, but natural log does increase. So as you go to infinity, it very slowly heads towards infinity, but it goes there. So what we get here is equals infinity minus, now plug in 1. What's natural log of 1? 0. So where's this thing headed to? Infinity. So it turns out that this area is infinite. And the reason is because this one is not dropping towards 0 fast enough. 1 over x squared gets small faster. So fast that the area is finite. These are somewhat.
The way I got one, but I approached it like instead of looking from the left to right, I
Mhm.
approached the right to left, which is one, so it's gonna stop at one. Maybe. I guess that I got the right answer.
Well,
See? Instead
Mm.
of looking from the left for the x squared, right, 1 over x squared, instead of looking from the left to the right side, with the approach of 0, right, I looked at it from the right side to the left because that's the endpoint. It's the highest point, and it's just 1. So no number is going to go over 1. The final answer is going to be 1.
I don't know. I have to understand. I don't understand the logic behind that. We'll talk about it. Let me finish this up.
That's what I was talking about when he was explaining the derivative of e to the x. He added up all of them, and it was like e to the x over e to the x is 1 plus x squared over e to the x. So this goes really small. Same concept.
Yeah, I'm a little off there. I don't know what y'all are referring to, but okay. All right. So look, tonight I will send you an email. It won't be a quiz, I promise. It'll be a homework though. Okay, because now I can finally pull some problems out of the book that I like. There was nothing up to this point out of the book that I really cared for, but now these are going to be pretty mechanical problems that you're going to have for homework. All right. But do your homework. And be prepared for a possible quiz on Thursday. Possible.